I'm Anil Kumar, and in this video, we'll try to understand the value of imaginary numbers when they are multiplied by themselves. I, as you know, is the imaginary number iota, whose value is square root of -1. So if you square I, that means I square is -1, right? So that helps us to solve many quadratic equations where within the radical square root sign we have negative numbers. So they kind of expand our working with numbers. Now let us explore further what happens when we are working with higher powers of this imaginary number I. That is to say, what is I cube, what is I to the power of 4, what is I to the power of 5, and does it have any kind of a pattern? So what we know here is I square root of -1, I square is -1, I cube will be equal to I square times I, right? So I square is -1, so we get minus I to the power of 4 could be written as I square times I square, which is -1 times -1, and that is equal to the number 1. Now when you get I to the power of 4 as 1, this is a very important relation. Let's mark this. I to the power of 4 is 1. Now if I have to find I to the power of 5, it is better for me to write this as I to the power of 4 times I, correct? Since I know that I to the power of 4 is 1, so that should be equal to I. Now this helps to calculate any power of I. For example, if I say what is the value of I to the power of 20, then we know 20 is a multiple of 4, right? 4 times 5 is 20. I could write this as I to the power of 4 to the power of 5, right? That gives me 20. And since I to the power of 4 is 1, I could write this value as 1. But how about I to the power of 21? In that case, we could have one component with power of 4 like we had earlier, and we could multiply that by 1. So it is now the power is 21. Since we know that the first part is 1, the answer is I. Do you see that? So that really helps us to calculate any power of I, right? So let's take a few more examples here, and then we'll also see how to represent this on a graph, right? So if I write I to the power of, let us say 30, 35, okay. Now we know that I could be written as 32 is a multiple of 4, so I could write this as I to the power of 32 times I cube, right? Now I to the power of 32 is I 4 times 8. Is it okay? And then we have I cube. Now what you see here is that the first term is 1 and multiplied by I cube will give us the value of I cube, which is equal to minus I, right? So you could write minus I from here, or you could go one more step, I square times I or minus I. Anyway, what we see here is that this pattern of I, which is that I to the power of 4 is equal to 1, right? I to the power of 5 we just saw is I. And if I calculate I to the power of 6, it will be I to the power of 5 times I, which is -1, right? I to the power of 7 will be multiplying -1 by I, which will give us minus I. And then 8 is a multiple of 4. Then again the pattern repeats, right? So what you see always is that the pattern of I powers can have one of these 4 values. That is to say, it could have 1, I, -1, or minus I as the values, correct? This is one very important aspect. The other thing which we can also see from here is what is sum of 4 consecutive powers of I. Sum of 4 consecutive powers of I. That is to say, what is I plus I square plus I cube plus I to the power of 4? Well, as you have seen here, I is, we could write this as I, right? I square is minus 1. I cube is minus I. And I to the power of 4 is plus 1. And when you add all of them, you get 0. And that is always true. Let me take any other powers and you can explore on your own. For example, what is I to the power of 30 plus I to the power of 31 plus I to the power of 32 plus I to the power of 33. So if you take any 4 consecutive terms with I, their sum is always going to be equal to 0, right? So you can evaluate powers and check for yourself. Now in the coming videos, we will also see how to represent the complex numbers on a graph. So let us look into these values of I on a graph also. So in a coordinate plane, we represent real numbers along the x-axis. So the x-axis represents the real numbers and the y-axis represents the imaginary numbers. This is I. So let us say this point here is 1, then this will be I, right? And on the left side of this origin, we have minus 1, and downwards we'll have minus I. So that is how we can represent imaginary numbers on our imaginary plane, right? So here we have to the right real numbers on the number line, right? Vertically up and down, we represents the imaginary part. Let us see how these values can be represented here, right? I. When I multiply I by I square, what do I get? I square is minus 1. So I square is this point, right? How about I cube? I cube is minus I. So this could be written as I cube. And I to the power of 4 is 1, right? Then you come back to I. So what you see is, as you multiply I with itself, it kind of rotates counterclockwise. That is how its value changes. Do you see that? So that is a cyclic pattern which we observe in the powers of I. So that gives you a good understanding of how the value of I changes when we multiply it by itself. It could have one of these values, and if you take any 4 values together, consecutive numbers, you come back to the same position from where you started. And so their sum is 0, right? It's one full circle. I hope this helps you to understand how the value of I changes, the iota, imaginary part of a complex number, when it is multiplied by itself, the pure imaginary part. I'm Anil Kumar, and I hope that helps. Thank you, and all the best.